So today I will talk about our SOC paper, parameters of fault adversary models connecting theory and practice. And in this work, we consider a fault attack countermeasures within symmetric key cryptography and specific to ASICs. And in this work, we propose a parameterized fault adversary model that encapsulates the control span of an adversary over an ASIC board. And based on this model, we investigate how well the theoretical assumptions made in countermeasures and fault attacks align with practical realities. Let's start with the fault attacks. So fault attacks are active type of physical attacks against implementations of cryptographic algorithms. They actively disturb the computations through physical means, such as clock voltage glitches, EM waves, or laser fault injection. And then the adversary observes the reaction of the device to these injected faults. So the device can give wrong output after these injected faults, or device can give no output at all, which might be suppressed by the employed countermeasures, or the device can still give a correct output. And all these reactions are exploited by the adversary using some mathematical analysis methods. So a fault attack simply consists of two stages. First, the physical fault injection into the circuit. So in this part, an adversary takes the circuit and they make some changes in the values in the circuit. And these changes are followed by the mathematical analysis of them. So in the context of fault attacks, we use the term adversarial model to define an adversary physically injecting a fault to an ASIC board. So this model tells us that the adversary injects this fault to this location in the circuit, and this fault has this type of effects in the output. And similarly, the fault analysis methods have some assumptions regarding the physical fault injection adversary. So these assumptions tell us that if an adversary injects this kind of fault, so if they realize this kind of fault scenario in the circuit, then using this technique, we can exploit it to retrieve some secret information from the circuit. And now we also have some countermeasures which are proposed against these fault analysis methods. And these countermeasures are also based on similar assumptions. And what they say is, if an adversary realizes this kind of fault injection scenario in the circuit, then we make sure that, or like with high probability, we make sure that the adversary cannot get any secret information from the circuit. So these both fault analysis methods and the countermeasures are based on some assumptions regarding the physical fault injection adversary. So in practice, an adversary, by using a physical fault injection mechanism, can realize extensive fault injection scenarios in the circuit. But as we will see in the presentation, the fault analysis methods leverage only a fraction of the capabilities offered by those injection mechanisms. And each fault analysis method depends on some certain properties of the injected faults. So this makes it a bit hard to assess the security of the cryptographic implementations. And also similarly, we have some countermeasures which are proposed against the specific fault analysis methods, but not the practical capabilities we can get in practice. So it's a bit hard to get the general view, like what we have in practice and what are the threat vectors and how much we make use of them and how much we protect against them. So in this work, as a step to solve this problem, first we make use of some new terms, and we use a physical adversary model to define an adversary who is injecting a fault into circuit physically, an analytical adversary model to define an adversary assumed in the analysis methods, and a mitigative adversary model to define an adversary assumed in countermeasures. And then we propose a parameterized adversary model that encapsulates the control span of an adversary over an ASIC board. So with this model, what we wanted to do is just to describe all these theoretical and practical adversary models using a unified adversary model. And then based on this model, we analyze the differences in between these theoretical models and practical models, and then see how well actually we protect against them, or how well we make use of the practical capabilities. So this is the parameterized fault injection adversary model we propose. We have the following parameters, and these parameters help us to precisely model the physical adversary. And we have a number of fault injection events. This is the number of times the adversary is injecting a fault to the circuit using the injection mechanism. And this becomes handy when the adversary is injecting multiple faults to bypass a countermeasure, for example. In the fault location, the adversary can have precise, loose, or no control over the location. Precise control means the adversary is able to target a specific gates in the circuit. Loose control means the adversary is targeting a set of or cluster of gates in the circuit, but which ones will be affected is unknown by the adversary. And no control is just, there's no control over the location. And fault timing is also similar. With the precise control over timing, the adversary can target a specific clock cycle or specific operation in the circuit. And with loose control, again, the adversary can target a set of operations or set of clock cycles, but which one will be affected is again unknown. And again, there is no control. And number of affected bits is the number of directly affected bits by the fault injection. Duration of the injected fault can be transient, persistent, or destructive. And transient fault is effective until the original value is recovered by the circuit. Persistent fault is effective until the original value is explicitly overwritten. And destructive fault, it just destroys the physical layer, so you cannot access the original value again. And the targeted gate type, it can be combinational gates, memorial gates, or like both of them can be targeted. And fault type can be a set fault, which changes the value to 1, a reset fault, which changes the value to 0, a flip fault flips the value of the variable, a random fault, or a custom fault. A custom fault defines an adversary who can change the mapping of the gate to their choosing. So now we have the overview of the proposed adversary model. And now let's see what we have in practice when we map the physical fault injection mechanisms into this adversary model. And the first mechanisms we have is clock and voltage glitches. And they both affect the longest critical path in the circuit. Clock glitches, they shorten the clock period. And the voltage glitching, it increases the propagation delay of the transistors. So in the end, they both disrupt the full propagation and stabilization in the circuit, which gives us some wrong values appearing in the circuit. So by using these two mechanisms, an adversary cannot really target a specific location in the circuit, because which gates will be affected is dependent on the input of the circuit and also the underlying circuit at that time of the fault injection. So it's not possible to choose a specific part in the circuit. And then we have EM fault injection. This is electromagnetic waves. And this causes a race in between clock and input signals. And this might result in some faulty sampling at the registers. And using EM fault injection, an adversary can target a part in the circuit, but the waves can inject faults to more gates than originally intended. But still, this has higher spatial resolution than glitching mechanisms. And then we have laser fault injection. And using this mechanism, an adversary can choose specific gates in the circuit, and they can even inject the faults they want. For example, they can choose to inject flip fault in the specific gate. So it's the strongest one among all of them. And now let's see the general view of these injection mechanisms. So the first thing is that target location is fixed when you use these fault injection mechanisms. They are not adaptive throughout the encryption. And we can target only a few locations in the circuit. So they can do several fault injections, and they can even do that within the same clock cycle. And they last several cycles. So when we map them in the adversarial model, then we could see that we can actually put them into two groups. And one with high precision and small target area, and one with low precision and large target area. And the ones having high precision and small target area, so they can target the specific gates in the circuit, and they can also inject specific fault types. So they can choose the fault type as set, reset, or even the custom faults. The thing is that the number of bits that are affected by the fault injection is upper bounded. So you can't really inject a lot of faults at the same time. And we can give laser fault injection as an example to this group. The second group, having low precision and large target area, they affect more adjacent gates than the originally intended. And there's no upper bound in the number of bits affected by the fault injection. The adversary can only inject random faults using these mechanisms. And as we have seen in the previous slides, we can give clock voltage glitching and EM waves as examples to this group. And now we have seen the model, we have seen the physical fault injection mechanisms, and let's move on to fault and combined analysis methods. And as I said, fault analysis methods are exploiting the injected faults in the circuit. And if an adversary makes use of the side channel information, then they become combined analysis methods. And now I want to show you three selected fault attacks. And the first one is differential fault analysis. In this attack, the adversary obtains one faulty and one correct ciphertext from the same plain text, but they, of course, apply it to a number of plain texts. And then they exploit the differential information obtained from this correct and faulty ciphertext. The second one is statistical fault attacks, SFA. An adversary injects a fault to an intermediate variable, and they introduce a bias, and then they collect the faulty ciphertext, and they obtain this intermediate variable from this faulty ciphertext. And what they see is, because of the introduced bias, the distribution of the targeted variable is non-uniform. So in these two fault attacks, or fault analysis methods, we make use of effective faults, meaning the fault is injected and fault is propagated to the output. So the fault didn't disappear to anywhere. And the third method, statistical ineffective fault attacks, SIFA, one of the most dangerous fault attacks. This makes use of ineffective faults. And ineffective faults are injected at some time in the circuit, and then they just disappear. So they don't propagate to the output, and they yield correct ciphertext. And SIFA actually works the same as SFA, but now it collects the correct ciphertext, and they obtain the intermediate variable from this correct ciphertext, and they check the statistical distribution. And again, they see that it's non-uniform, so it can be exploitable. So when we map the fault attacks, like a huge number of fault attacks, into the adversarial model, what we see is they actually demand only a fraction of the capabilities offered by the physical fault injection mechanisms. So what we see is the fault analysis methods mostly exploit a single injection, and they only affect the number of affected bits, whereas we have seen that they can actually affect a lot of bits in the circuit. And even more, the classical analytical adversary model assumes that there is only a limited number of faults affected, and the adversary can inject the fault type they want to inject. So they assume bounded attack order. And this is much different than what we can get from the physical injection mechanisms. And now we know the attack vectors, and let's see how we protect them against these fault analysis methods in theory. And the most common approach to protect against fault attacks is to use redundancy and masking together. So how we can implement redundancy is, first, we can just implement some error detection or correction codes. And this means the countermeasures should apply some error checks at certain times during the computation. So the thing is that if we simply combine redundancy and masking, then probably we're gonna miss the ineffective faults. So what we should do is we need to put error checks at every possible location in the circuit so that we can catch the faults before they become ineffective. In impeccable circuits, part TI and transform and encode are such examples. And another technique to implement redundancy is using MACTAGs. And there are two examples for this, M&M and Kappa. And what they do is they attach a MACTAG to each sensitive variable, so they can keep track of the changes made in those variables. M&M has a single check at the end. So as you can imagine, it doesn't protect against ineffective faults because those faults already disappear through the end. Kappa implements an error check for each multiplication. So as you can guess, it catches all the ineffective faults. And another method to protect against ineffective faults is to ensure error propagation. This is a slightly different approach. And there's a countermeasure from Jan Daiman, and they make use of permutations to make sure that if the input of a function is faulty, then the output is also faulty. And so they make use of Toffoli gates to implement a whole circuit to make sure that. And there's another countermeasure, StaTI. And in this countermeasure, a notion is proposed called stability, and which makes sure that all injected faults propagate to the output. So we don't miss any ineffective faults, and we can catch them at the end. So when we map the assumptions made in countermeasures to the proposed adversarial model, what we see is they really align better with the analytical adversary models rather than the practical capabilities we can have in real life. So they mostly assume the bounded order of attack, with exceptions kappa and MNM. So if an adversary can inject random faults, kappa and MNM has no order of attack. The adversary can inject a lot of faults. And another thing is there are some countermeasures which propose provable security, but they propose it within a restricted mitigative adversary model, which means they assume maybe up to 3 faults in the circuit, like 3 bits affected by the fault because of the efficiency reasons. So they offer limited protection against physical injection mechanisms. And on a different note, they also sometimes allow multiple and which are adaptive locations to be faulted. So this is over-designed because we have seen that we can't really do that with physical fault injection mechanisms. So this is extra overhead in the hardware. So what we can take from this presentation is, unlike such an analysis, we don't have any limitation in the number of fault injection events that we can do on the hardware. It might be the case that, probably it is the case, we don't really protect against physical fault injection mechanisms, and maybe even the fault analysis methods that are really easy to carry out in practice. But also it might be the case that we over-design them and we just put extra overhead in the circuit, so we do more than what we want to do. So what you can do is you can check the countermeasures you use, and then you can map them into the proposed adversary model, and then you can check our mappings of the fault analysis methods and the physical injection mechanisms, and you can see if they align with each other or not. And probably they don't align. Yeah, that was the end of this presentation. Thank you for your attention.
Hi, thanks for the talk. I have a couple of questions. What kind of overhead are we talking about here?
It's like a number of gates. For example, kappa is huge. You can't really fit it in a hardware because it's over-designed, because it protects more than what you would like to protect. It just makes it huge in the hardware, and it's slow. It needs a lot of resources, a lot of randomness.
And I may have misunderstood, but with the MAC authentication, often Macs will have like a similar, like the back end will be a kind of encryption, right? Like a hash or like. Mm-hmm. So if you have full injections in that circuit, why would they not be in the Mac? Does that make sense?
Yeah, they mostly assume that it is the setup phase, like where you generate the MAC tags of the sensitive variables, so they assume there are no faults injected. Yeah, so it's out of assumptions made in countermeasures.
It's like our scope. Do you think that's a fair assumption? Like, do you think that reflects like the adversarial model?
Yeah, that's interesting actually, because if you include everything, then you can't really protect against fault attacks, because you can just inject a fault at error check and then, yeah, well, you have correct output. Yeah, to need to implement some things in theory, then you need some assumptions regarding your fault injection adversary. Well, of course, it's possible.
Hi, thank you for the talk. I will follow up on that. So you looked at all these countermeasures and attack vectors. Is there any simple advice you could give? What countermeasure would be the best to implement against, I would say, a common attacker, or that doesn't exist?
Well, the easiest is to replicate the circuit, but it doesn't protect against ineffective faults. Now, the best solution would be implement error checks for each multiplication, which is super heavy, but then you can catch all the ineffective faults. I think MacText propose a good solution, not for ineffective faults, but in general, because of the randomness included in that, you can't really replicate the fault. Like, you need to know the MAC key in order to inject the same faults in both replicated circuits. So I think they propose good solution regarding that, but it's a question how efficient is that?
Okay, so there is no simple answer.
But for me, the best thing is to ensure the fault propagation, because you're sure that the fault is reaching to the output. So I think it's the neat solution to ineffective faults.
Okay, thank you.
Hi, I really enjoyed your talk. You mentioned that you have to choose between precision and target area size. Will that ever change as technology, or improve to where you can choose both rather than having to choose between?
Sorry, to choose in between what?
Precision and target area size for fault injection.
Well, it's actually, like, you want to affect a lot of gates in the circuit at the same time. Then you can't really do it with laser injection. So you're up to EM fault injection or clock voltage glitching. But then you can choose EM because it gives you higher spatial resolution. Then you can almost make sure that you can inject faults to the gates you want to affect. But other than that, yeah, what is available in practice is this, yeah.
Okay, thank you.
I guess that's it. Yeah.
Hi everyone, I'm Giacomo, and today I'd like to present you my master thesis work about threshold, post-quantum threshold signature based on cryptographic group action. So to introduce the topics, I made yesterday a little last time change to the slides because I decided that instead of doing like some boring timeline, I like to use directly the word of the panelists of Tuesday, the cryptography panel, really a wonderful panel and really inspiring. And so, like, citing them, both on the relevant topics for this talk, on post-quantum, they were discussing this and trying to understand what do we need to do and how do we, like, should handle this phase, in particular with the focus on, with different focus on encryption and on signatures, since on signature we have, let's say, more time, but we also need to explore more on them, to explore their reliability and what we can do with them. And also they spoke about multi-party computation and threshold as an important way to increase the security of the system, avoiding single point of failure, but also to preserve the privacy of the computation and of the users involved in it. So let's start finally with some science. And I will introduce a well-known tool that I think most of you know, that essentially take an identification protocol that is a primitive that allows a prover to show that he knows some kind of secret associated to a statement and render it to a signature using the so-called Fiesch-Emitter form from one of the panelists. And the core idea is that the only difference with the signature is that in a signature we also prove the knowledge of not only prove the knowledge of a secret key, but also that we approve a message. And to do that, the idea is that we have to incorporate in the challenge both the commitment but also the message. And we can do that with a cryptographic hash function that can actually be computed by the signer during the signature procedure, so that with this non-interactive procedure, it can actually generate a transcript that will become the signature that will be then verified by the verifier with additional recomputation of the challenge. So essentially the idea is that we just have to find the right indication protocol, and then we can get a secure signature. And in particular, here we would like to focus on threshold signature that are multi-party computation primitives in which essentially we split the knowledge of the key between any user in such a way that any T user can start an interactive protocol in which they compute a centralized signature that can then be verified against the known verification, known and common verification signature. So our main tool for this construction will be cryptographic group action. So a group action is a standard tool from mathematics, very well known, like I think from more than 200 years, and in particular very known to cryptography, because the core idea is that you take a group, you take a set, and you have the element of this group to act on the element of the set, so mapping set elements one to another in a way that is compatible with the group. And this one is essentially the core idea between the elliptic curve cryptography. In this case, like the set is an elliptic curve, while the group is the set of integer. And essentially, the operation is the multiplication by an integer. But clearly, this is a really nice model. In fact, it allows for a lot of construction. But it's not post-quantum resistant, quantum resistant. And so the idea of still using group action is to try to keep some of these generalities, some of this nice construction, but to avoid this quantum algorithm by essentially choosing a set X that doesn't have an additional structure, the structure of group, essentially avoiding the core step of the Shor algorithm, that is the combination using this additional operation that we have on the group, because like on elliptic curves, we don't only have the multiplication, but also we have the addition. And if we negate this operation, actually we don't know at the moment, and we don't think it is possible to have an equivalent of the Shor algorithm for a general group action. So suppose that we have this group action that we can manipulate. We need to make some hardness assumption on it, clearly to be used in cryptography. And in particular, we consider the generalization of the discrete logarithm problem, known as a vectorization problem, in which we ask the adversary essentially to given two set element X and Y to find a link between them, so essentially a group element that maps X to Y. Then there is the generalization of the computational Diffie-Hellman problem, in which we give the adversary the application of two group elements, and we task him, okay, now find the combination of them. And then there is the generalization of the decisional Diffie-Hellman problem, known as parallelization testing, in which essentially we give the adversary a bunch of pairs of set elements, and we ask him, okay, can you distinguish if they are like just like random elements in X, or they are actually parallel, so linked by the same group element? And this is known, yes, as parallelization testing problem. So if we have a group action that is actually resistant, in particular, we request that we are particularly focused on the group action inverse problem, the vectorization problem. We can actually write an unification protocol to show that we can solve this problem, or at least we are solving it for a pair, X and Y. And the idea is, it's very straightforward, like take X, the origin, apply a new group element, a random one, and obtain a commitment. And then you may be tasked or to show that you can link X and Z, or that you can link Y and Z. Clearly, if you can do both, you can also compose this link and get the secret G, and so you are able to solve the problem. So we have this unification protocol with standardized 1/2. We have to repeat it lambda times to get a lambda bit secure unification protocol. And with the Fisherman transform that we saw before, we can actually get a lambda bit secure signature. And now the point is to instantiate it. Okay, so we have to choose a particular group action. And the nice story with the group action is that we have a lot of them, They are really well studied. Clearly, there is the one from elliptic curve that is not quantum safe, but we have other of them. Here are listed 4 that are relevant for the NIST standardization process. And from different parts of mathematics, like we have from isogeny, but we also have some of them coming from coding theory for the problem of finding equivalence between linear codes, but also coming from tensor. And there are other into the studies coming from lattices, from polynomial systems, and so on. And as a brief comparison, before touching on threshold signature, I will just give you a benchmark like between different signature schemes submitted to the NIST call. And here we have like the classical one, let's say, based on the coding. Here we are focusing on the one based on coding theory that have a really nice public key, like they are just hashes, but relatively big signature sizes, while with the equivalence-based signature, like less and mets that are based on the equivalence of codes with different metrics, we have actually worse public key, but better signature sizes, in particular if you combine it with some optimization. And most importantly, at least in my opinion, is that we can have a lot of additional construction on additional functionalities for this signature that come out really in a natural way, like ring signatures, logarithmic linkable ring signature. We know them from almost 4 years, I think. But also we can have for any group action, actually threshold signature that we saw before, in essentially with minimal assumption on the group action. So let's see how to build them. It's a really standard construction, I would say really natural construction, that was already like written between the lines of some work on threshold signature from isogeny assumption, but can actually be generalized for any group action. So let's start with a simple case in which we have the threshold t equal to n. So we need all the users to participate in the generation of the signature. And how do they can share a secret that in this case would be the link between x0 and x3? And the idea is that take some group elements, each user take one group elements, and they apply them proceeding in order, starting from the origin. So they apply it on x0, that the first user gain x1, that is sent to the next one, that will apply again a group element, and so on up until the end, in such a way that in this way they get a public key, x and x0 and x3, and the secret key, that is the combination of this group element, is shared between them. Okay, so we are in this situation now. We need to start some kind of identification protocol to mimic the previous construction, and it's really straightforward how to do that. Like, just repeat the calculation with now random group elements, generate a commitment, z, and now if you need to show the link between x and z, the user just open their commitment secrets. Otherwise, they start a recursive and sequential procedure in which the first user actually link and x1 and z1. He can do that since this share and this share, and then send this link, this group element, to the next user that will combine it with this secret share, the link received, and the secret share associated to the commitment to obtain the next link between intermediate elements, and so on up until the end, obtaining actually the response link in the commitment to the other part of the public key. And this can actually work for any group action. We don't need to request the group action to be abelian. We don't need to request it some particular assumption. Just we can actually combine the element in a straightforward way. Like we can multiply them and invert them. Okay, so now the point is, how do we make this secure in the malicious user model in which like some user may try to misbehave from the protocol? First of all, we need to make sure that during the generation phase, if we are in the distributed case, no user is like trying to tamper with it. For example, the last user can, for example, try to just generate an element starting from x0, or you could even try to bias it, like choose a particular group element in such a way that, for example, the first bit of the public key is 1. And in principle, it shouldn't be possible to do that. This shouldn't be possible. So the solution, already individuated in sashimi, but here generalized to any group action, is to have the user commit at the start of the protocol to a particular group element, by essentially applying it on the origin and then having them to use that particular group element again during the key generation as secret share, and showing that not only that they know these particular links, but also that these links are parallel. And to do that, essentially, they do the parallel version of the previous protocol, in which they create a parallel commitment, and the responses are, again, parallel both for the challenge 0 and both for the challenge 1. So intuitively, like, if this is parallel and these are parallel, also this one would be parallel. And okay, so we have a zero-knowledge proof for the property that we like. Clearly, it is to be noted that here we have not just a pair, but two pairs that are parallel. So we need to make the additional assumption that this doesn't leak information. And sadly, there are some, for one particular group action of interest, that is the linear equivalence, one that we get from linear equivalence of code in the dynamic metric. If we take a particular choice of parameter, this actually is not secure. It recently came out of work on it, but it's really like a specific attack for a particular choice of parameters. It has to be noted, but it's not that worrying, in my opinion. And so, okay, we have this distributed key generation. Now, suppose that we are in a situation in which we can actually, like, or we have a trusted party, or we have used a distributed key generation to get the sharing of the key. We need now to render the protocol actually to a signature with the VHDMI transform. But if we do that in the plain way, like just apply it, we encounter a problem, because again, the last user may try to tamper with it. For example, he can behave honestly on the first lambda -1 execution, and on the last one, he may try to choose a particular group element in such a way that he can bias the challenge output. For example, he can force a particular bit to be 1 or 0. And this actually, if you are in a concurrent, if you are allowing concurrent signing, this can actually lead to a forgery of a signature in a way that is similar to the attacks to blind signature, to the attack to Ross attack or parallel Ross attack. So we need to solve this. And a possible solution that was proposed for abelian group action is to use, again, a lot of zero-knowledge proofs in the same way as in distributed key generation. While for the distributed key generation, this would be OK, now it's not OK anymore, because like we have to do lambda zero-knowledge proofs for any user, for any signature. That would make like completely impractical. So we need to invent something different. And our idea was to use a secure randomness on which the user have to commit at the start of the protocol. Then they do the commit and generation, and after that, they recompute the randomness, and they incorporate it in the challenge evaluation. In this way, in the quantum random oracle model, it's not possible anymore to tamper with it, and can actually be used if we add an additional verification at the end to show that the security of this signature, even in the malicious user model, reduces to the security of the centralized signature. And so we actually have finally a secure and out-of-n threshold signature, even in a malicious user model. And now we need to make it, we actually need to make it T out of n, so for make it possible, not only in the case in which all the users are requested, but also in the case in which less users are should be allowed to produce a signature. And for the abelian group action case, it was already shown in this work that it's possible to do that with linear secret sharing. This has some problem. In fact, the zero-knowledge proof becomes more and more difficult, but still doable. But there is an additional problem that we cannot perform anymore this particular check, since we don't know the intermediate element. And so we need to rely, again, in that case, at least they show it that they need to rely on additional zero-knowledge proofs, really complicated zero-knowledge proof, in my opinion, that actually make objectively the protocol unpractical. And also there is the elephant in the room that this solution is only working if the group action you're considering is abelian and has a particular shape. So, for example, you don't have any small prime dividing the group order. So we try something more general, known as replicated secret sharing. This is a really standard techniques in which instead of trying to modify the shape of the share, you increase their number and you assign a knowledge to each share to a particular user. I don't want to go into details, but it's really simple to generate, to use this technique, and can actually be used even for more general access structure, not only the threshold one. But here, I'll just give you an example for the case 2 out of 3. So suppose that these 3 users want to share a secret in such a way that any 2 of them can recover it. And the idea, they consider this subset, and for each of these subset, they create a share, and they repeat the standard generation procedure. And now, no user can actually compute all the path between x and x3, x0 and x3, but any 2 users, for example, user 1 and user 2, can combine them in such a way that they will be able to produce a signature since they know all the intermediate path during this work. So, like, we have finally a T out of n threshold signature for any group action. And so I'd like to conclude with 3 final remarks. First of all, that, yeah, as I just said, we have a T out of n threshold signature, but the number of shares increases exponentially with T and n. So we should actually check, is this still practical for real use cases? And the answer is actually yes. We tried to do some calculation, some benchmarking. And for the most likely situation that are like 2 out of 3, 3 out of 5, but also, for example, 5 out of 8, you can actually compute the numbers, and you see that using clearly some optimization, that you get something practical that can actually be used. These are like simulation done taking the parameters for the NIST submissions, and also with some recent optimization that can actually be applied for this particular choice of group action, so less and meds. Second, the other remark would be on the take-home message that I found funny. All the industrial presentation have this apply slide, so I've inserted it also myself. And here I have 2 messages to try to use cryptographic group action. We have seen their cons, we have seen their pro, and we have seen that they have a lot of flexibility, a lot of possible uses, and can be actually instantiated in a different way, and probably there's a lot of research to be done on them. And also on multi-party computation protocol, like threshold signatures, we have seen that it's true they are tricky to be used. You should use them in a careful way, look closely at the proofs, but when you do that, it's possible to have secure instantiation on them with also different flavors for the specific use case and you have in mind. And third, like I just want to point out briefly about the possible future direction that would be to try to apply some kind of linear secret sharing on also for more general group action, even for example if they are not abelian. Also, we would like to combine the Soltic techniques with linear secret sharing that at the moment we actually is not possible, but maybe it's by paying some price with some zero-knowledge proof should maybe possible. Then we're also working on trying to get distributed key generation, secure distributed key generation that doesn't use the additional assumption of parallelization. And we think that this should be possible. And yeah, but we want to be sure. There are a lot of the tricks to be, details to be studied. And then recently came out some work on threshold signatures since they are gaining a lot of interest. And so we should also investigate if these, some of their results can be applied also here. For example, masking used in threshold raccoon may be interesting, in my opinion. So thanks. Any questions?
Hi, thank you for the talk. You mentioned in the conclusion that you are moving away from the parallel version of the inversion problem, but do you believe that besides linear equivalence, it's still a meaningful assumption for other group actions?
Yeah, I think that it does make sense. For example, for a Abelian one, is not a problem. Like there are some reduction between the problems that will show you that is actually not a problem. You don't need to be worried about that. While like the reason why for linear equivalence it was broken is that essentially it was possible to get a lot of linear equation, and for a particular choice of parameter, you were lucky enough that these linear equation were almost undeterminate, and then you were able, like, by some kind of brute force, to close this gap. So it's like was really a likely spot in which we were able to break it. So I think that I tried to look at other group action and see if it was possible to do that, and actually we're missing too much linear equation, so I don't see a meaningful way. And so I think that in general, since there is a lot of difference between them, I don't think this to be possible in for any group action, at least in a straightforward way. I would be surprised.